Hey everyone, how's it going? Today we're going to be taking a deep dive into an RCNN. Okay, so now that I've said that, there must be two things on your mind. So, what the hell is an RCNN, and are you going into this specifically? Those might not be the only two things on your mind, but from where I'm standing, those are the two things I'd like to explain. So, what is an RCNN first? Well, an RCNN is pretty simple. It's a region-based convolutional neural network. Happy? No, I'm sure you're not. So, okay, what is it actually? Right? We know it's a region-based convolutional neural network, but what the hell does that even mean? So, convolutional neural network is basically for object classification. So, to identify if something is an object. What the region-based aspect of it allows it to do is it allows it to be a lot faster. So the actual real model is called a Faster RCNN ResNet 50 with ResNet 50 support or something like that. It's things like ResNet 50 with FPN support, something like that. Yeah. So it's like, well, what is that? So, well, region-based proposals. What is our region-based proposal network or RPNs? So, a region-based proposal is basically, so how this model works is I'll get into depth in this in the next video that I post, which I'll actually be going into depth on a paper I wrote about this topic. So what the objective that we're doing is, let me identify some things. So the objective that we're doing is we're training a faster RCNN object detection model to detect the numbers on Uno cards. That's basically what we're doing. And the way that it works, very simply, is let's say I take a photo of my face and I want to identify if the person in this photo is wearing glasses. What it'll do is they'll take the photo. Maybe we have the photo, we input it through our data set, whatever, we configure it. Now, what's going to happen is there will be regions determined on this image. So we'll identify this part of the glasses, we'll identify my face, and we'll basically, the algorithm will determine different parts of the images it finds interesting or has lots of features. And what it'll do is then it'll use that CNN part. It'll use the object classification part. So we've determined these regions in this photo, and now we're going to determine what is in these regions and then figure out which region to look at in an image that allows for us to identify the model the fastest. That's basically what a region-based convolutional neural network is. I hope that made sense. If you guys have any questions, please feel free to leave them in the comments below. And also, if you have any trouble understanding the terminology, maybe you don't understand what the word dire is or directory means, search it up, please. Feel free to learn on your own. ChatGPT exists, Google exists. Feel free to obviously go through it on your own. Check out the code. That's how I went through it. I feel like that's the best way to go through it. You go through the code, ask some people, watch a few videos, understand what's going on, and then start to slowly work on it. Well, anyways, let's get into the code. So since we're doing a little overview, we won't be going too depth into the terminology, but we're going to be looking at the process, how the pipeline works. So again, first step, what are we doing? So, well, it's the config.py file. So what is the config.py file? It's basically importing PyTorch. It's determining different things like the batch size. This is basically like how fast the RCNN will run based on the amount of GPU memory that we give it. Resize underscore to is basically to resize the images and make sure that they're all normalized at a specific pixel. 416 by 416, I think that's what we used. Number of epoch. So what is an epoch? It's basically running like an iteration of the data set. So it's gonna have 10 iterations through the data set in this model. Device. So this is basically basically what is a device? It's like, so it's a variable that's like set up to this device for training. So it's like either using the GPU or the CPU depending on the availability of a CUDA compatible GPU. That's just what they use, CUDA. But It's basically determining, is there GPU available? No? Okay, well, we won't use it. Oh, there is? Okay, we'll use it. Basically, that's what it is. It's not difficult. Also, number of workers, we set it to 0 because we want this to be able to work on any device. That's also why the batch size is a little lower. Classes is basically number of Uno cards there are. There's 14 if you didn't know. There's 14 cards in the deck. Now you know that. Visualize transform images, true. So we want to see the images after we've transformed them. And transformations, we're not changing the images, we're just adding an annotation. So let's say we have the card 6, it's going to be a little red circle, 6, and we'll identify it. That's what visualizing a transformed image will be. Train directory, this is very basic stuff. This is just figuring out how, like just configuring the files, right? This is standard stuff. Next step in the pipeline is datasets.py. So datasets.py, this is an interesting file. It's basically setup stuff as well, but it takes care of two things, or a couple things. So it'll read the images and the corresponding XML annotation files. So already went over the annotations, and so it'll also pre-process the images. That's the interesting part. So it'll resize them, it'll convert the color format. It's basically just normalizing them. You know, some of the examples of things it might do is like flipping the images, cropping the images, color jitter, just to make sure that all the images are normalized and they all work. And not that they all work, because they all will work, but all of them won't change the results that the model should experience, and it won't mess up the loss function, or it won't mess up the values and the efficiency too much. That's basically why we normalize these images. We want to have a data set that works for our use case. It is also just data augmentation stuff. It'll create the data loaders and set up the data loaders and the data set. Actually, you can see that over here. I think it's done. Yeah, so we create the training data set validation set, create the training loader, validation loader. One important aspect of this code, most of it's very simple. Well, you know, we're importing from config, import from torch, custom utils import. This is another file that we'll go over in a bit. You know, we are initializing, we're getting the item, we're getting the picture, right? And we're going to resize the picture. We can go through and see this code. It's pretty self-explanatory, I feel like. But one area that I'd like to cover, because sometimes people don't throw it in there, is basically at the end of the code, there's a script. And this script, if you run it on its own, you run it standalone, it will visualize some sample images and their annotations using the custom data set. The reason that we threw this in there, and the reason I'm talking about it, is because it helps ensure that data set pipeline is working correctly. That is something that's important for us to do. We want to make sure that what we're working on is working correctly, and that's what this does. So I thought I'd go over it for a little bit. And again, in summary, basically this code just sets up the data set and the data loaders, and it'll be used during the training and validation process, basically. Let's go on to the next step. So what's next? Model.py. Great stuff. Now we're getting into the good stuff. So the model that we're using. So a little brief overview of a Faster RCNN. So what does it use? What are the techs, the technologies that are employed in this endeavor? Okay, so it uses a region proposal network. I've talked about this before, RPN. So it generates the candidate bounding boxes, or the candidate object bounding boxes. So object, find out which areas have the most interesting stuff going on, basically. RPN. I go into it again in the next video or in the paper. Just check out either one. Pooling. So pooling also, of course, happens. It happens in every network. Pooling basically extracts the fixed size feature maps from each candidate region. So it'll take a specific size of a feature. So we have a candidate region. Let's say the candidate region is my face. Now we've determined that the glasses, this part of the glasses is very important. Okay, well, it'll identify, maybe this part of the glass and maybe this part of the glass. That's basically what the pooling will do. It'll pool them all together and figure out what is the important regions of the image to look at. it pools it. It doesn't actually do the checking which part of the image. It does the pooling part. So like collecting all that stuff and finding out, basically the extraction process, right? That's what pooling is. So that's a very simple explanation, honestly. It's like fifth grader explanation. Please, ChatGPT, Google, figure it out on your own. Yeah. Something else that happens is the classification head. So it also predicts the class label, and it just refines the bounding box coordinates. So like, as we can see here, there's like Faster RCNN, ResNet 50 FPN. What does that even mean? Some parts of the code you might not understand. So, what is the role of ResNet 50 and FPN? So, basically, the model does, it extracts high-level semantic features from the different images. It also, like, we're creating the model. We are loading this is pre-trained, by the way, so it's from PyTorch, but we're loading the pre-trained Faster RCNN with ResNet 50 and FPN, feature pyramid network. That's what FPN means. And we're also modifying the model's head. So like, we're modifying this model's head to match the number of classes that we have. So the target number of classes and the model's head need to be the same for our model to correctly figure out which card number these cards are. So we're basically just creating the model, making sure that it will work because we've set the number of heads that the class has to the number of classes that we have in our target database. And that's basically what we're doing here. We're basically just doing setup stuff. So we're creating a model. And this is going to determine some custom utilities that we're going to be using in this process as well. I think the model.py is a little bit of because this is a very short piece of code, but there's a lot of stuff that happens, right? So we're importing, we are creating a model. The model is now going to be equal to Torch Vision's pre-trained model, and then we're going to figure out the number of features or heads, the number of input features that we need. So there's 14 different input features, right? And we're defining a new head for the detector with the required number of classes. Sorry, the number of heads is 14. The number of input features, I'm not sure. But this is getting the number of input features from the actual model. Yeah, so the number of heads is going to be equal to 14. Sorry about that. So that's basically, and we're returning the model just to make sure that it's all set up correctly so that we're able to use it in the training. And then we're going to go custom utils. So the averager class, there's a couple different things that go on here. So let's go through it one by one. Of course, your imports. And yeah, so basically the imports we're importing, albumations is kind of an important one. Most of the stuff you can search up and figure out what exactly these tools are. So actually, let's just go over the functions, yeah. So averager, it's basically a class that helps keep track of the average value for training and validation loss over multiple iterations. So to figure out the exact average validation loss or training loss over the entire thing, we can use that. That's what averager for, is to help determine that for us. Save best model. Oh wow, please save the best model. Pretty obvious, right? Save best model. What does it do? It doesn't save the best model. If it didn't, it would be crazy. It does save the best model. Collate _fn. This is kind of an obscure. What says it? Yeah. Well, so you can read this file, figure out exactly what everything does. Honestly, these utility functions and these classes are basically just going to be used in conjunction with the previously defined configurations, just in order to build and train and validate the RCNN model. This is, again, functions. This is just a class of pure functions. But yeah, let's get into training. So this is the fun part. So what goes on in the training? So of course we're gonna get imports in. Basically what's being done is the train function. The train function, it iterates through the training data set. Right here, it iterates through it. It zeros the optimizer gradients. It moves the images. Yeah, it's a target. Yeah, so it moves the images. I'm not going to highlight the exact parts because some of them are. Yeah, oh, actually, it does. I think I'll say it in order. So it zeros the optimizer gradients. It moves the images and targets the computation device. It calculates the loss using the model's forward pass. So forward pass is a term that we use in like machine learning. Honestly, it's better if you search it up because it is kind of a complicated thing. And again, I don't want this to be like a 2-hour video of a tutorial. So let's just keep going through it. If I did that for everything, I'm sure there's a bunch of things like optimizer and gradients that I haven't explained. But again, ChatGPT, Google. I don't want this to be a 2-hour video. I don't want to waste your time like that. And honestly, it's better if some things you learn on your own, so you have that database of knowledge for yourself. Okay, so we're also using back propagation. Again, complicated topic. So there's some complicated stuff that we're talking about here. So it's good if you have a depth of knowledge before you continue into the next video, especially because we're going to be talking about some more complicated stuff. But yeah, so we're going to back propagate the loss and update the model parameters. Actually, I'll quickly explain back propagation. So basically, when we're looking at the mathematical graph of a function, let's say we're using, it depends on which, okay, for back propagation, let's say we're using a sigmoid function. We have our loss function, and our back propagation, what it will do is it'll take whatever value we have for our loss, and it'll back propagate to find the lowest possible, what is it called? It's a local minimum. So it'll back propagate to find a local minimum, and that will be the lowest possible loss function that's mathematically possible for our what do you call it? For our model. So if we train it and we use our math to figure out what's the lowest loss, and we calculate it mathematically one side, and we train it another side, and we find out that our training loss is a little higher than our validation loss. So that these are two different things that we do use. So there's validation loss, training loss. So if we find out that our training loss is higher than our validation loss, we'll be like, okay, so why is it higher? Why is our model performing worse than we expected it to? And then you can figure out troubleshooting wise mathematically what's going on. We can look through the code as well. It's basically a way to make the program more efficient. We talk a little bit more about that in the next video. So we'll check that out later, or you guys can check that out later, or read the paper. The paper does a great job of explaining the stuff too. So it back propagates the loss and it updates the model parameters. It does SDG optimization with momentum and weight decay as well. We use I'd say there's a robust and effective optimization algorithm in place here as well. And then the weight decay, it's basically regularization to prevent overfitting. Overfitting is basically when the program only works specifically well for one use case scenario. So it'll only work for our data set. It won't, if we throw in new photos, it won't be able to do the new photos. That's what overfitting is. You never want a program to be a model to be overfitting to a use case scenario because it's practically useless at that point. Especially if you're employing this in like real world scenarios where people won't have the same picture from your 10,000 picture data set. That's what's gonna happen in the real world. People are gonna take new photos of an Uno card, and your program's gonna have to be able to identify it. And if it's overfitted, it won't be able to identify it. And now you have a faulty product in your hands that you've wasted a bunch of time on. So that's why we want to use regularization and weight decay, the weightage of each node to prevent overfitting. And the next function. So validation. So this is the validation function. So we're going to, again, same thing, iterate through the data set. We're going to move the images. We are going to calculate the loss. we are going to evaluate the model, see how good it's going, like how good is this model. We're gonna assess the model's performance on unseen data. So we're gonna throw in photos, and we're gonna be like, what is this? And it's never seen it before, and it'll have to identify it, and we'll be able to assess its performance based on that data. And again, we're going to be preventing overfitting by monitoring the validation loss and making sure that it's performing well on unseen data, right? And then we have our main loop. So if name. So what's the main loop? So it basically initializes the training and the validation data sets. So yeah, right. Initialize them, and it iterates through the specified number of epochs. I think, where is that done? I don't see it. There it is. Yeah. So for the number of epochs, it's going to iterate through. It'll perform a couple of different tasks. So one thing that it'll do, it'll reset the training and validation loss histories. It'll run the training and validation functions for each epoch. It'll save the best model so far, and that's the one with the lowest validation loss. And it'll save the current model after each epoch as well. And then it'll sleep for 5 minutes. Yeah, it has to take a break, man. You can't have this model running 24/7. It's gonna kill itself. It has to sleep for five seconds at least after each run, and that's basically the complete thing. So again, the project is basically to identify numbers of Uno cards, and it saves the best model based on the validation loss. That's basically what the entire model does. And now we have a model that can identify Uno cards correctly. So I don't have one on hand, but if you did and you took a photo and you threw it into the model, it'll identify it. And that's basically the explanation of the code. It's a nice little overview that we've just done. And next video, again, that'll be when we go into depth of the paper, the mathematical stuff, what's actually going on behind the scenes. So stay tuned for that. Thank you very much. Signing off, Abdur again. Hope you guys have a great day, and take care.